In previous class, we are discussing about the what is measurement, okay, what is the instrument, okay, what are the types of instruments, okay, and what are the essential requirements of an instrument. Okay, there are must and should this having the this instrument having the three essential requirements. Those are damping torque, okay, controlling torque, as well as the deflecting torque. So here the deflecting torque is produced by using the magnetic effect or electrostatic effect. Those are seen in previous class. So in controlling torque, the controlling torque is provided in two ways. That is the controlling torque is two types: spring control, gravity control. Okay, by providing the springs in the instrument, you have to produce the controlling torque in this one way by using the gravity. Okay, by using the gravity here you can produce the controlling torque in another way. Okay, so here in spring control, okay, so in this is the arrangement of a spring control. Okay, so this is the outside view. So all of you seen in this outside view in voltmeters, ammeters. So this is a scale, this is a pointer. Okay, so in top side on the outer view you have to see this scale and pointer. Okay, inner side, okay, in the inner side you have this connection. That means to move that pointer. So controlling torque is nothing but it controls the deflection. Okay, it controls the deflecting torque. Okay, that means always the controlling torque or deflecting torque in opposite position. Whenever the system is in a steady state, okay, at equilibrium position, constant position, at that time the controlling torque is equal to the deflecting torque. Okay, so that's why this is the arrangement of a spring controlling torque. So in this you have a one balance weight to the pointer. Here you have to provide a two springs. Okay, see here to support this pointer on the upside here you have to provide a dual bearings. Bearings is nothing but to support that pointer. Okay, so here you have to spindle. Spindle is nothing but a one stride. So this total is a spindle. That means one pot. Okay, so upon this spindle you have to connecting a springs, two springs A and B. These are called control springs. So whenever you have to given the supply, at that time first the pointer will be deflected and it will gives the values. So controlling torque means it controlling the values. So at that time the springs will move up and down. Okay, spring action will be stop now. So at that time it can stops the pointer. Whenever the pointer will be stops, at that time you can take accurate reading. Okay, in controlling torque always, so the pointer we moves is nothing but a deflection. Here you get the value. Here you can say that in terms of measurements point of view, you can say that is deflection. So here in the spring control, the controlling torque TC, here the controlling torque is denoted with TC. The controlling torque is always directly proportional to the deflection theta. See, advantages. Advantages of a spring control system. The instrument can be placed in any position, that is horizontal as well as vertical. Okay, so here you can arrange in the horizontal position or in vertical position. Okay, so this method does not increase the weight of the instrument as springs are light. Okay, so here you are using the spring control. That means the controlling torque is provided by using the springs. So that's why, so this so in this method the weight of the instrument is also less. Okay, scale is uniform. Okay, here you can take a uniform scale is nothing but, so you are seeing in MC type you have to mention MC and MI. So spring control is always used for MC. MC means uniform scale. Okay, uniform scale means if suppose you can take 10 amperes meter, 1 to 10 readings it will be indicates 1, so remaining 1. So in between middle you have to 10 small lines. So at that time you can take 0.1, 0.2 like this. So at that time the scale is uniform. Okay, so disadvantages. So coming to the disadvantages of a spring control, temperature variations. Okay, the variations in the temperature can affect the length and design of the spring. Okay, so whenever the temperature will be increases, at that time here spring means the spring is made with any one material. So at that time it can affect the a length of the spring, and hence also changes the controlling torque. So it also changes the controlling torque value. Okay, springs get deteriorated with the time, and hence accuracy is also lost. So whenever so many times you have to use the meters, at that time the time is also more, so you have to use. So at that time you have to, so at that time the springs may be damaged, so at that time the accuracy, so the whenever you have to take in the readings, at the time you have to miss the accuracy. So next, coming to the gravity control. See, this is the arrangement of gravity control. Okay, see, this is the gravity control system. Okay, this is a pointer. Here you have to scale. So if maybe you have to indicate it or not. Okay, so here you have to scale, and this is the pointer. Here same spindle. This is the control weight, and here you have to balance weight. Okay, see. See here control weight. So control weight means, see, initially whenever you have to start the experiment, so at that time the pointer will show readings. Controlling that means it controls. So whenever the point will moves continuously, at that time here the control weight. Okay, so the control weight acting upon this pointer, and that time it gives it will control the values. That is nothing but the gravity control. That means here depending upon the gravity. Okay, so here here the you can control the controlling torque. So that's why here controlling torque is equal to W sin theta into L. Okay, so see, when deflected by an angle theta, the weight exerts a force, that is W sin theta. So see here in previous diagram, see here the spindle. Okay, whenever because of this gravity it experiences a force in this direction. So at that time, so that means here from this point to from this here in this position the pointer will move. At that time it will give the deflection theta. So that's why here it exhibits a force W sin theta. So controlling torque is also called as a restraining torque. The restraining or controlling torque is developed given as, so Tc equal to W sin theta into L. L means this length. Okay, here you can take this in the form of a triangle. Okay, at that time this is the length of the pointer. Okay, so Tc equal to W sin theta into L, that is equal to, so since TD is always deflecting torque is always proportional to the current flowing through the meter. Okay, so in any meter, so deflecting torque TD is proportional to Y, and I will say that at equilibrium position. Okay, so Tc equal to TD. So at that time W sin theta is equal to T. So here TD is proportional to I. So whenever you have to remove this proportionality constant, at that time this is equal to TD equal to Ki. So in this place TD you can write Ki. So at that time I is equal to W by K sin theta. I is proportional to the sin theta. That means here the current flowing through the meter is proportional to the sine of the angle. So that is in the spring gravity control. But in spring control, Tc is directly proportional to theta. That means Tc is directly proportional to always I. So at that time theta is proportional to the I. So advantages. Okay. Coming to the advantages, it is simple and cheap. Okay, and it is not affected by temperature variations. So here you cannot use any spring or not. So that's why. So here this is works on depending upon the gravity only. So that's why it is not affected by temperature variations. Coming to the disadvantages, here the scale is non-uniform. Non-uniform means I think you are seeing in the EM2 lab MI instruments. So in MI instruments, MI voltmeter or ammeter, any MI wattmeter, the scale is non-uniform. Okay, the system must be used in vertical position only. Oh, here the system only placed in a vertical position. So this arrangement may cause parallel axis error. Okay, that's why this causes the parallel axis error. Okay. Next, the essential requirement for the instrument is nothing but damping torque. So the damping torque is provided in three ways: by using air friction damping, fluid friction damping. Okay. So the next one is eddy current damping. So in fluid friction damping, see like this. The arrangement is like this. Here pointer, you having a here spindle, through spindle, pointer, scale. So inside, okay, inside this pointer is given in a one airtight, one tightening air chamber. Okay, that means in this you have a one piston. Okay, so see here, total in the chamber you have to place a 8. So whenever the pointer will be moved, so at that time the piston will goes upward side. Okay, that means pressure increases. So pressure moves in the upward side in the air chamber. Okay, so at that time, so whenever, so sorry, damping torque is nothing but so see, whenever in sometimes whenever you have to take a reading, if suppose you have to take in 10 amperes. Okay, so if suppose the pointer is at 10 amperes, is not constant. So at the time it oscillates to and fro, forward and backward directions. So at the time to make the pointer at that constant position, you have to require a one torque. That is nothing but the damping torque. So that means to stop the pointer. So whenever the pointer will be oscillates, so at that time the piston will move downward direction. So moves that in downward direction and it will stops the pointer. Okay, that is the purpose of air friction damping. That means here you are using the one air chamber. Okay, here by using the air chamber you have to provide the air friction damping. Okay, so next one is what? Fluid friction damping. So the name itself indicates. So in air friction damping, you have to by using the air chamber. In a fluid friction damping, you have using a one fluid. See, you have to take me one vessel. So in this vein or so here you have to place a some oil. Oil is nothing but some fluid. You have to one vein disc. So you have to, this is the spindle. Through this spindle on top side you have to pointer and a scale. So see, so whenever the pointer will be moved and that time the vane and disc is also rotated. That means moving upward and downward direction. So whenever the pointer will be oscillates, at that time the disc moves upward direction and constant the pointer. So that is nothing but the fluid friction damping. So here by using the one fluid, you can stop the pointer. Okay, that's why this is called a fluid friction damping. Next one, eddy current damping. Okay, by using one damping magnet. Magnet is nothing but, okay, if it exists a magnetic flux. Okay, through this magnet you have to place a one disc. Through this disc you have to spindle, you have to arrange a pointer. Okay, so whenever at initial position these aluminum disc is in outside. Okay, so through the magnet. So whenever point will be moved, okay, this is completely goes to inner side. So whenever the pointer will be oscillates, so at that time also, okay, because of the magnetic flux, these aluminum disc will move outside and stops the pointer. Okay, this is the arrangement of a eddy current damping. So why this is called eddy current damping means here you are using a one damping magnet. Okay, that's why this is called as a eddy current damping. Next one is voltmeter, ammeter. Okay, an instrument which is used to measure the potential difference or voltage between 2 points in the circuit is called voltmeter. Okay, an instrument which is used to measure the potential difference or voltage, okay, between 2 points in the circuit is called voltmeter. Ammeter, ammeter is nothing but an instrument, okay, an instrument which is used to measure electrical current in the circuit. Okay, so is called ammeter. Okay, so in the voltmeter is nothing but it measures the voltage between any 2 points. So if you take any circuits in between any 2 points, you can measure the voltage, that is called voltmeter. Ammeter is nothing but an instrument which is used to measure the electrical current in the circuit is called ammeter. Differences between ammeter and voltmeter. See, there is no difference in the operating principles of ammeter and voltmeter. That means the operating principle, okay, the operating principle of ammeter and voltmeter is same. Both are current operated device. So both are current operated. Whenever the current, so whenever you have to give in the supply, whenever the current will flow through these 2 meters, at that time only these 2 meters will be working. Okay. So deflecting torque is produced when the current flows through the coil. So that means whenever the current will flow through the coils, at that time the deflecting torque will produce, at that time shows the readings. An ammeter can be converted into a voltmeter by connecting high resistance in series with. So ammeter and voltmeter is same. So whenever you have to connecting a one high ammeter, you can convert this ammeter into voltmeter when by connecting a one high resistance is in series with this ammeter. Okay. Okay. See, types of instruments used for voltmeter and ammeters. Okay, so the practically used ammeters and voltmeters can be the following three types. Okay, here mainly we are using the three instruments. Okay, three instruments are used for voltmeters and ammeters. Okay, that means construction. Okay, so that is permanent magnet moving coil type, PMMC type, moving iron type, electrodynamometer type instruments. So you have to do the experiments in missions lab. In missions lab, you are taking, you can write operators. Okay, operators in a observation book or in a, you can write in the sleep, you can write MC and MI. Okay, so here you can discussing what is the MC type and what is the MI type. Okay, the types of instrument used for voltmeter and ammeters are three types. Those are permanent magnet moving coil type, moving iron type, electrodynamometer type instruments. Okay. See, first one is PMMC instrument. Okay, this is very important. Okay, so PMMC is nothing but permanent magnet moving coil instrument are used for measurements of DC quantities. Okay, that means only you have to measure. So whenever you have to given the per meters to the DC, those are called DC instruments. So that means these are used for only DC quantities, that is DC voltage and DC current. Okay, this is the construction of a inner side. Okay, PMMC. So this is outer side view. Outer side you have to see the pointer. Okay, and you have to see the scale. Okay, so on top of this pointer you have to see the mirror. Okay, below you have a one small mirror. Okay, this is the arrangement of a this is the arrangement of a PMMC instrument. Here you have to take a two magnets, permanent magnets. In these magnets you have to place a one core. Okay, so this core is surrounded by a one coil. Okay, through this one you have to provide a one spring. Why? Because here you have to using the spring by providing here controlling torque by using a springs. Okay, so that's why you have to here using a spring. So for this pointer you have a ball balance weight. Okay, to balance this one here you have to connect a GL bearings. Okay, see the basic principle of PMMC instrument. Okay, the basic principle of PMMC instrument is Lorentz force, d-orthogonal movement. That is, when a current carrying conductor placed in a magnetic field, a mechanical force existed on the conductor. Lorentz force equation is nothing but whenever current carrying conductor, any current carrying conductor is placed in two magnets, that is in the magnetic field, a mechanical force is exerted on the conductor. See, here same. So, coming to this diagram, see, this is a one conductor, current carrying conductor. This is placed in two magnets, N and C. Whenever a current will flow through this conductor, so at that time, whenever magnetic field will be exist, at that time the current will flowing through the conductor. At that time, this conductor current will deflect this pointer. At that time, this deflector will shows the reading. That is the working principle. Okay, that means the PMMC instrument is working on the Lorentz force equation. So for this pointer, again you have to provide a damping torque, eddy current or spring torque. Here you have to providing a spring control. So that's why you have to indicate the springs. Okay. So the spring, see here, the spring provide the controlling torque as well as the incoming and outgoing leads for the current. See next one, the aluminum farmer provides the eddy current damping to damp out the oscillations. So here you have to see in diagram, you have to place a farmer. Okay, this farmer is nothing but aluminum farmer. By using this aluminum farmer, here you have to, so here must and should, any instrument you have to apply a damping torque, controlling torque and deflecting torque. Here the controlling torque is provided by using the spring, and here the a damping torque is provided by using a aluminum farmer. That means here you are provided a eddy current damping. So here you have to provide a eddy current damping for the magnet. See. In the PMMC, you have to producing a deflecting torque. Okay, it can be proved that the deflecting torque is given by, here the deflecting torque is produced is D equal to BINA. BINA. So BNA is nothing but, here you have to take in a one constant G. So see, here B is nothing but magnetic flux density, I is nothing but current, N means number of turns, A means area of the conductor. Here you have to total expressed as the here, so it can be proved that the expression for the deflecting torque is given by TD equal to, so that means this is direct expression. Okay, for the current carrying conductor, this is from the Lagrange force equation. So this I think you have to study in this, I think in missions or somewhere EM1, I think this formula will be get torque equal to BIAN. So here you have to take BNA as a constant, GI. So this is the deflecting torque produced in the PMMC. The controlling torque is given by C equal to K theta. Why? Because here you can write C equal to K theta. So here you have to providing the controlling torque by using springs. So in spring control, the controlling torque is proportional to the deflection theta. So at that time here you have to write TC is directly proportional to theta. So you have to take in, you have to remove the proportionality constant. So at that time you have to write TC equal to K theta. Okay, for steady state. So here direct have to write TC equal to K theta. So if you want, first here you have to write TC is proportional to theta, and you have to remove the proportionality constant, and directly you can write TC equal to K theta. So for steady state, at steady state, the controlling torque is equal to the, I will say that at steady state or equilibrium position, the controlling torque is equal to the deflecting torque. So at that time TC equal to TD. So whenever PMMC is in steady state position, TC equal to TD. TC means K theta, TD means GI. So here KK will be, KG both are constant. At that time theta is proportional to I. So and that means whatever the deflection, whatever the current will flows through the meter, corresponding to that gives the deflection. That means here it provides a uniform scale. So that means the deflection is proportional to the current flowing through the meter in the PMMC. See advantages. Advantages and disadvantages of a PMMC instruments. Advantage, coming to the advantages, it consumes less power. Okay, so it consumes less power and has great accuracy. So accuracy is also high. It has uniform divided scale. Already I will say that here that deflection theta is proportional to the current flowing through the meter I. So at that time it has uniformly scale. Okay, next one, the PMM has a high torque to weight ratio. Okay, here torque to weight ratio is high, so that it requires less current. So at that time high torque to weight ratio, so it requires less current. It can be modified as ammeter or voltmeter. Okay, so it can be used as either ammeter or voltmeter. Very effective and reliable damping is possible because of eddy current damping. So here you have to using the damping torque is provided by using the eddy current damping. So at that time, so here the eddy current is very effective and reliable method. So okay, so these are the advantages of a These are the advantages of PMMC instruments. Coming to the disadvantages of PMMC instrument. Here in first, so in first starting PMMC, I will say that it is only used for the DC supply only. Okay, so cost is costly cost. So cost is high compared to the MI type instruments. So next you have to discussing moving coil iron instruments MI. So compare those moving coil iron instruments. So the M3 instruments are costly. Errors are caused due to the friction, temperature, and aging of the control spring. Here you have to provide the controlling torque by using the springs. Okay, so when so these I will say that so in a spring control also, whenever there will be variations in the temperatures, okay, at that time the spring may be affected. So at that time, so it causing the aging. So whenever so at that time due to the friction of the spring, temperature, and aging of the spring, so that means whenever the age of the spring will be increases, at that time it causes the errors in the instruments. Okay, this is nothing but the so next to second type instruments is moving iron instruments. Okay, MI instruments. Okay, see, moving iron instruments are used for the measurement of both AC and DC quantities. Okay, these moving iron instruments. Okay, these moving iron instruments are used for the measurement of both AC and DC quantities. Okay, here you have two types of moving iron instruments. Are you have to use mainly two types of instruments. Those are attraction type and repulsion type. Okay, here so PMMC instrument is used for only for DC quantities, but here the moving iron MI instruments are used for the measurement of both AC and DC quantities. Types of moving iron instruments. Here the moving iron instruments are mainly two types: attraction type, repulsion type. So coming to the okay, this is the construction of a attraction type MI instruments. Okay, so see here you have to taking a one balance weight. Okay, so this is total balance weight. Balance. So this W1 and W2, W3 are the control weights. Okay, so here you have placed a one moving iron disc. Okay, magnetic disc. You have to place upon this magnetic disc. You have to placing a different weights. Those are called control weights W1, W2, W3. Okay, here you have to providing a air. So here you have to by seeing this diagram you can say that here you have to providing a air friction damping. Okay, and here you have to a piston. Okay, so here you have to use a gravity control. Gravity control. Okay, see, this is the here you have to play from this disc. You have to place a but you have to place a pointer, and on the balance weight here you have to place a coil. This is having the coil winding. Okay, so coming to the operation of this attraction type MI instruments, see, so whenever you have to giving the supply, okay, so at that time here the disc will be rotated. Okay, so at that time whenever the disc will be rotated, so this having the controlling weights. Okay, so at that time controlling weight. So here why you are using the controlling weights W1, W2, W3, these are providing the gravity control. Okay, so that means here you are using the gravity control to produce the controlling torque, and you have to using a air damping chamber. So why? Because it produces the air friction damping. So whenever at a time these all forces will be acting, the pointer will move and gives the readings. Okay, for balancing of these all, here you are using a one balance weight. Okay, this is the construction and operation of a attraction type MI instruments. Okay, coming to the repulsion type. Okay, these are the repulsion type instruments. Okay, see here also you have to using a field coils. Okay, two field coils. Here in these two field coils you have to place this is a fixed vein and this one is a moving vein. Two veins will be placed, and here by these two veins you have to giving a spindle. Through this spindle you have to connect a pointer, and here you have a uniform scale. Okay, on this spindle here you have to place a spring. Okay, by using this spring here you have to provide a controlling torque. Okay, so here see these are the magnetic force induced by the field flux. Okay, so see here see by so in I will say that in previous I will say that why this is called moving attraction type means whenever you have to giving the current, so this is a coil and this is a one magnetic disc. So at the time this magnetic disc, this coil winding both are will be attracted. Okay, attracted, and it will deflect the pointer. That's why this is called attraction type instruments. So repulsion type instruments means, see here you have to place a same poles N, N, S, S. So so this one is fixed, this one is moving. So whenever you have to giving a supply, so at that time the field will exist in the this field coils. So at that time the current will so at that time the magnetic field exists in these two veins. At that time NN, that means same poles was attracted or repelled. Same poles will be repelled. Okay, repulsion will take place in between these two veins. So at that time it will move this side. So at that time it move upward direction. Okay, and it will deflect the pointer. This is nothing but the repulsion type MI instruments. Okay, so those are the repulsion type MI instrument. This is the working. Here you have to provide the controlling torque by using the springs. Torque equation. So coming to the torque equation of MI instruments. So you have to write the torque equation for MC instruments. From this you can obtain theta is proportional to the I. So coming to the torque equation of MI instruments. So let here I here you can, so for this you can assume some assumptions. Let I equal to initial current. DI is nothing but increase in current, that means change in current. L equal to inductance. DL you can assume change in inductance. Theta is nothing but deflection. D theta is nothing but the change in the deflection. Okay, see increase in applied voltage. So E equal to D by d theta of Li. Okay, so that means rate of change of current. So here you can write this is in the form of UV. So at the time here you can write I dl by dt plus L into di by dt. The electrical energy is applied. First initially you have to giving the electrical energy. Okay, so that electrical energy supplied is EIDT. So here you have to supply the electrical energy is IDT. So that means, so here that is equal to the, so EIDT. So here see, whenever you have to differentiate this one, so at that time this is equal to the I square dl plus IL dA. So this one, the stored energy changes from, previously I will say that you can assume I equal to current, IL equal, so the stored in the energy is nothing but half Li square. But here the change in the current will be changes from I equal to di, and the inductance is L is changes to dl. So at that time you can write I plus di whole square L plus dl square. That means the stored energy changes from half I square L to half I plus di whole square into L plus dl. Okay, hence the change in the energy. So this is in the form of A plus B whole square. At that time this will be expand. So that at the time, so that means the energy stored from changes from this one to this one. So at that time the change in energy means this minus this value. So at that time you can write half. So this can expand A square plus B square plus 2AB L plus DL minus half Li square. So at that time neglect, so at that time this one we multiplying with these two one, okay, and expand, and after expansion you can neglect second and higher order terms. So I will give the material. In the material in between this you have to deep expansion, okay, so that means you have to expand, so and neglect higher terms, so you can neglect higher quantities, higher terms, so at the time the remaining values here you can occur IL DL plus I square DI, sorry, I square DL. Okay, so that means here the stem. That means so I understood how you can get this one. So actually the electrical energy is supplied this one. Okay, the change in the energy will be given in the instrument is given by IL DI plus I square DL here, right? So how to get this one means from this total from this derivation. Okay, so at the time from the principle of conservation of energy. Okay, law of conservation of energy, electrical energy is supplied is equal to the increase in stored energy plus mechanical work done. Okay, this is the law of energy. So at the time energy, the electrical energy is supplied at the time, here you can write EI dAT equal to I square VL plus IL DI. So at that time here you can write I square VL plus IL DI is equal to increase in the stored energy. So increase stored energy. So increase in stored energy is given by ILDI plus half I square DL plus mechanical work means deflection. So movement is nothing but the mechanical work. So at that time it can write TD d theta. So here plus, so mistakenly this will here so equal to is mentioned, but here plus. So at the time ILDI, this ILDI will be cancelled. So at the time I square DL equal to half I square DL plus TD. So whenever you have to put this side I square DL minus half I square DL. So at the time here you can get, you can take LCM these two terms, at the time you can get half I square DL is equal to TD d theta. So from this you can write TD equal to half I square DL by d theta. So that is nothing but this is the deflecting torque of a MI instruments. But here controlling torque. Here controlling torque is given by TC equal to K theta. Okay, so TD equal to half I square DL by d theta. Controlling torque equal to TC equal to K theta. At equilibrium position, TC equal to TD. So that means TC equal to TD means TD is half I square DL by d theta. TC means K theta. So these are total half DL by theta is a constant. Here K is also constant. At that time theta is proportional to the I square. That means here the deflection in the MI instrument is directly proportional to the square of the current which is flowing through the instrument. That means, but in a PMMC instrument, the deflection is proportional to the I. Okay, that means that deflection is proportional to the current flowing through the meter. Okay, so that's why there will be, the scale will be uniform in the PMMC instrument. But here the scale is non-uniform in the MI type instrument. Why? Because here the deflection is directly proportional to the square of the current flowing through the meter. Okay, so that is the torque equation of a PMMC. See here. I will say that here you have to directly write it. So expansion already here. See here. I will write the expansion. So expansion. So how to get this stored previous MI type instrument? So increase in applied voltage E equal to DL by I theta. So from this here you can get I DL by dt plus L di by dt. The electrical energy supplied EID by equal to IL DL plus L di by dt into IDT. And why? Because here in the place of E, I will write this one. So that's why here you can get E di by dt equal to I square DL plus IL di. Okay. So మీకు అక్కడ డైరెక్ట్గా అర్థం అవ్వదని నేను మళ్ళీ ఇక్కడ పేపర్లో రాసి పెట్టానమ్మా, కేర్ఫుల్గా చూడండి. సో ఎనర్జీ స్టోర్డ్, సో ఎనర్జీ యాక్చువల్లీ స్టోర్డ్ ఎనర్జీ ఈజ్ ఈవన్ హాఫ్ LI square. So the stored energy will be changes to, I will say that L plus DL plus I plus DI whole square. So at the time change in stored energy. So actually stored energy this one. So this one changes to this one. So whenever you want the change in stored energy, at that time you can write E2 minus E1. So at that time half L DL plus I plus DI whole square minus half LI square. So at that time this is in the form of a plus B whole square. So you can write this one. You can cancel all these terms. So at that time here you can get Remaining value here you can miss. See, from the law of conservation, electrical energy is supplied equal to increase in stored energy plus mechanical work done. So hence mechanical work done is nothing but force into distance. So at that time here you can write TD d theta. So previously here you can write. So electrical energy supplied. So from this C, here the electrical energy supplied is I square dl plus IL di. So from this here the change in the stored energy is given by IL di plus half I square dl. So ikkada miss ayindamma, ikkada కనిపించట్లేదు, half I square dl. Okay, so here IL di will be cancelled. So here I square dl plus ikkada half I square dl plus d theta. Whenever you can pass this side, this half is the same terms. Same terms means you can take LCM. You can take LCM here. You can get half I square dl, TD d theta. So at that time you can write TD equal to half I square dl by half I square dl by d theta. So you know controlling torque formula is TC equal to K theta. So at steady state, always at a steady state, TC equal to TD. So that's why you can write K theta equal to half I square dl by d theta. So from this theta equal to half I square K dl by theta. So here total half K dl by d theta both are constant. So at that time here you can get theta is directly proportional to the I square. So that means the deflection is directly proportional to the square of the current flowing through the meter. Okay, that's why here you can say that here the scale is non-uniform. See, coming to the advantages and disadvantages of moving iron instruments. So I will startingly I will say that it is suitable for AC and DC measurement, but PMMC instrument is only suitable for the DC measurement. But here the moving iron instruments are suitable for AC as well as DC, and it having good accuracy, cheap in cost compared to PMMC instrument. So this is coming as a disadvantages in a PMMC type. PMMC is high. So but here MI instrument cost is low compared to the PMMC instrument. Okay, these are the advantages of a moving iron instrument. Coming to the disadvantages. Okay, coming to the disadvantages. Okay, the power consumed by the instrument is high. Okay, so compared to that permanent magnet moving coil instrument. Okay, the power, the supply, electrical supply, whatever you have to given is more for the MI instrument compared to the MC instrument. Okay, and here the scale is also non-uniform. Why here you can get the scale is non-uniform? Here the deflection is directly proportional to the square of the current flowing through the meter. Okay, these are the advantages and disadvantages. So in next class we are discussing about the electrodynamometer type instrument.